This video is all about estimating the size of a population using a method called capture-recapture. And you might come across this in biology if you haven't already. Before we dive into the example, let's start with this problem here. We've got two boxes, box A and box B. Each one contains 1,000 marbles. Now, one of these boxes has got 800 red and 200 blue marbles, and the other box has 500 of each colour. We've got no idea which one is which though. Now, what you do is you shake box A to make sure the marbles are all mixed up. So it's not like all of the red marbles are at the top and the blue ones at the bottom or anything like that. The marbles are completely mixed up. You then pick 20 marbles without looking from box A, and you find that you've got 17 red and 3 blue marbles. Now, based on this information alone, do you think box A is the one with 800 red and 200 blue marbles, or is it the other box with 500 of each colour? Which one do you think it is? And can you be absolutely sure that it actually is the box you're thinking of? Well, based on the information we've got, it would make sense to think that it is the box with 800 red and 200 blue marbles. Because in our little sample of 20 marbles, we've got way more red than blue. So it's probably this box here with way more red than blue marbles. However, we can't be sure. It might still be the other box, and just as a matter of chance, we might well have picked 17 out of the 500 red and 3 out of the 500 blue. It's possible, but it's much more likely that it's actually the other box, the one with 800 red and 200 blue. Can we try and be a bit more convincing? Well, yes, we can. Let's take a look at this information. So from our sample of 20, what we've really got is 17 20ths of those marbles are red and 3 20ths are blue. Now I can turn these into percentages. This is 85% red and 15% blue. Let's look at the original information. Well, this box here is 80% red and 20% blue, whereas the other box is 50% red and 50% blue. Now, if we make the assumption that our sample is representative of the whole population, then we can expect that the whole population has about 85% red and 15% blue, which is pretty close to this here. So the assumption we're making is that our sample is representative of the whole population. Let's move on to the example for this video. Jane is trying to estimate the number of trout in a lake. Trout are a type of fish. She catches 150 of these fish, attaches a tag to each one, and releases them back into the lake. So she doesn't just capture these fish and take them away, she puts them back into the lake still alive. She goes back to the lake and catches 120 trout. She finds that 48 of these 120 have the tags that she previously attached. Using all this information, Jane is able to estimate the trout population of the lake. How does she do this, and what assumptions need to hold for Jane's estimate to be reliable? Let's start from the beginning. Jane is trying to estimate the number of trout in the lake, so this population, and we don't know what this is to start with, so let's just call it N. And what we'll need to do by the end of this question is come up with a number for N. Next, we notice that she catches 150 trout out of the total population, which is N trout. And what I'm going to do is work out what fraction of the trout get tagged. So she tags all of these 150 trout that she catches before putting them back into the lake. That means this is just saying that 150 over n of the population gets tagged. Now, 2 days later, she goes back to the lake and catches 120. So this is a sample of the population, and she finds that in this sample, 48 have got tags. That means the fraction of the sample that has tags is 48 over 120. And this fraction can be simplified to 2/5. What we can do is assume that the sample is representative of the whole population. So in other words, what we can do is say that because 2/5 of the sample has got tags, that means approximately 2/5 of the whole population also must have tags. In other words, the fraction of the population that's tagged must also be 2/5. I'm just taking this fraction here and putting it there. And now we've got an equation we can solve. We already said the fraction of the population that got tagged was 150 over n, and this fraction here must be equivalent to this fraction here. So all we need to do is solve this equation to work out what n is. Now, hopefully you're familiar with how to solve equations like this. If you're not, make sure you're watching this video on BossMaths.com and have a look at the interactive activity just above this video where you can practice solving equations like this, including ones with even nastier numbers. Solving this equation, then, we end up finding that n is 375. So 375 is our estimate for the number of trout in the lake altogether. Finally, let's look at what assumptions we're making to come up with this estimate. Well, we're assuming that this sample is representative of the whole population. We are assuming that just because 2/5 of the sample has got tags on it, that means approximately 2/5 of the whole population must have been tagged in the first place. So 150 over n must be roughly equal to 2/5. However, this might not always be the case. There are various reasons why your sample might not be representative of the whole population. For example, it might be the case that some trout are just easy to catch. This would mean that the easy to catch trout would be more likely to get tagged in the first place, and then when you go back to the lake to catch trout, you're more likely to find that those have already got tags on them, which would make you think that quite a high fraction of the trout have got tags, when actually there might be loads of really difficult to catch trout, all swimming maybe deep down at the bottom of the lake. We're also assuming that the population doesn't change much in the 2 days. For example, imagine a load of trout die between when Jane first catches the 150 trout and 2 days later, or maybe a whole load of new trout are born. By the way, if you are wondering why Jane leaves a 2-day gap, this is to make sure that the 150 trout with tags get a chance to mix up amongst the whole population again. This is a bit like the problem with the marbles in the boxes. Remember, you shook box A to make sure that the red and blue marbles were all well mixed up. So your sample then was more likely to be representative of the population. Similarly, before she goes back to catch the 120 trout, she wants to give the 150 trout a chance to get mixed up amongst the whole population. One more thing before we get to the end of this video. you can always check your answer for the population estimate. All you need to do is check that these two fractions are indeed equivalent fractions. So I'll do that up here. We just need to check that 150 over n, now n being 375, actually does simplify to 2/5. And what we can do is spot that 75 goes into 150 and also into 375. And if you divide the numerator and denominator by 75, you find indeed that the fraction does simplify to 2/5. So yes, we have solved this equation correctly, and n equals 375 is a good estimate for the total population. Now, this 375 is only an estimate for the population. It's not necessarily the exact population. And that's because we can't be sure that this sample we take here is perfectly representative of the whole population. But the idea is, if we are careful with how we pick our second sample, for example by allowing the trout to mix up and by having a reasonably large sample size, then this sample should hopefully be reasonably representative of the whole population, if not perfectly representative.